I want to calculate the limit of 1 minus cosine x plus square root of 3 sine x over e to the x minus 1 plus sine x as x approaches 0. So let's observe this limit to see what's going on here. So as x approaches 0, what happens to the top is that cosine x approaches 1. So 1 minus 1, 0. And so this also approaches 0. So we have 0 on the top. So we have e to the 0. And that's 1 minus 1, 0, 0 plus something that's approaching 1. So we have 0 over 0 type. So it's an undetermined form. So I'm just going to use one of the many other ways. So I'm just going to prove this theorem first. Then we're going to calculate that limit. So what I mean by f1 is approximately equal to f2. So this is what I mean. So let's say if we have a function f and g, f of x, g of x, let me just use shorthand. f, g, h, right? So mapping from real number to real number. So let's say if we want to calculate the limit of x approaches some x naught. So f times g. Right? All we have to do, if we have the following condition, if we have limit of x approaches x naught of, let's say, g, so g over h is equal to 1. So that's what I mean. So when I say, so some function is approximately equal to some other function as x approaches x naught. So what I mean by that is g over h is approaching 1 as x approaches x naught. Then I can denote it as g is approximately equal to h as x approaches x naught. Right, so in the context of infinitely small, if g and h both approach 0, then I say g and h are equivalently infinitesimal as x approaches x naught. Maybe x naught is 0 or some other constant, whatever. So in that case, we can just simply replace g with h to calculate this limit. So all we have to do is to calculate the limit of x approaches x naught of g f times h. Right? The reason is because f times h can be written as f times h times g over g. Right? And what is, so all I have to do is to look at, so I'm going to just write g, so f times g, right? I have h over g. Right? Like I said, given the condition that the limit of g over h, in other words, h over g, is also equal to 1, then we have this limit is going to be approaching 1. Right? So what do we want? Right? So all we have to do is we want to calculate f times g limit. Right? So given that if we can calculate the limit of f times h, if this limit exists, then since this limit is 1, then this limit is easily just the same as this limit. So we're done. So this is called equivalent substitution. Right? So it only works if it's multiplication or division. May not work if it's addition or subtraction. Because I'll explain why. So example. If we just substitute whenever we want, mistake might happen. For example, if we want to calculate the limit of as x approach 0 of x to the power 3, let's say perhaps sine of x minus tangent to x, right? Since we know that, for example, we want to determine the speed of tangent to x when it's approaching 0. At what speed? So tangent x is simply sine x over cosine x, right? So since when x approaches 0, cosine x approaches 1. Great. Sine x approaches 0. So I say tangent x approaches 0 maybe at the exact same speed as sine x, right? Simply because tangent x over sine x can be written as 1 over cosine x, right? If we let x approach 0, right, what's going to happen is the right-hand side is going to approach 1, right? So meaning the limit of tangent over sine is really equal to 1 as x approaches 0. So meaning really tangent x is really equivalently infinitesimal to sine x when x approach 0, right? So they approach 0 at exactly the same speed. Now, if we just recklessly replace tangent with sine, what's going to happen is that it's going to turn into sine x minus sine x over x cubed, right? If we want to calculate this limit and then we calculate this limit, right? All of a sudden, this limit, we can just ignore the bottom because the top already becomes 0. Right? That's where the mistake is. Now, this limit is not 0 because somehow we, by replacing tangent x with sine x, what we did is that we somehow changed the speed of the top, because we don't know what speed the top is approaching 0 at, right? Somehow we've changed into something that's approaching 0 very, very fast. How fast? It's outright 0, regardless of whatever, right? So we've drastically changed the speed of the numerator at which it's approaching 0. So that's why we have this mistake. Right? So what we're going to do in the correct way is we're going to perhaps use Taylor expansion to break tangent into something that's more obvious. So that's more precise. We're going to determine exactly what speed it has, right? So maybe also use Taylor expansion on sine x and finally determine its order of infinitesimal at the top. But I'm going to discuss that later. Now I want to prove that the limit of this stuff over that is equal to 1 as x approaches x naught, given these conditions. So let me just verify that f1 plus g1 over f2 plus g2, is it approaching 1? Right? So I can just, because I want to relate f1 with f2, because given this condition, right, maybe I can just minus f2 plus f2. Right? Likewise, I can minus g2 then plus g2. Right? So it's still the same thing. Minus f2 plus f2 plus g1 minus g2 plus g2. Right? So f2 plus g2, right? So we realize that we have f2 plus g2 on the top, same as the bottom, right? So they just become 1. Still, I have to use this and that and group this and that. So let me just break them apart. f1 minus f2 over f2 plus g2 plus g1 minus g2 over f2 plus g2. Like I said, I have f2 plus g2 over f2 plus g2. So they just become 1. Right? So that is equal to, perhaps now I can, because the given condition says what? f1 and f2 are equivalent during the process of the limit, right? So maybe I can just take this and divide. Maybe I can just first factor out f2, or just maybe divide by f2 straight away. Therefore, I can have f1 over f2, right? It says f1 over f2 approach 1. So this is what I'm going to do. So divide f2 on the top. I have f1 over f2 and minus 1. Right? Again, divide by f2 on the bottom. I have 1 plus g2 over f2. Right. So likewise to this, maybe I can divide by g2, right? g2. So g1 over g2 minus g2 over g2, 1. And f2 over g2 plus g2 over g2, 1. Plus that 1. So I realize that on the top I have f1 over f2. It's given to approaching 1. Given to be approaching 1. So 1 minus 1, I have 0 on the top. So what's going to happen on the bottom is that doesn't really matter, because we're given that f1 over g1 does not approach negative 1. Right? So therefore, since f1 over, so if we want to work out the limit of f2 over g2, right? All we have to do is to work out the limit, like I said, equivalent substitution, right? f2 equivalent to f1, g2 equivalent to g1. So f1 over g1, right? It says does not equal to negative 1, right? Right, so meaning this cannot approach negative 1, right? So we cannot have 0. So the bottom cannot approach 0, right? So likewise, g2 over f2, right? g2 over f2, just flip them upside down, still cannot approach negative 1. So this bottom cannot approach 0 either, right? So meaning we cannot have an undetermined type of 0 over 0. No, we won't have that. So we're safe. So what do we have is we have 0, right? That's top approaching 0. Bottom does not approach 0. Maybe it'll approach some constant, non-zero constant. Maybe 1, maybe negative 5, whatever. Maybe the bottom will approach positive infinity. Maybe negative infinity. Maybe bounded. Maybe no limit. In either case, the whole fraction is going to approach 0, because the top already approaches 0. Right? The bottom does not approach 0. So anyway, so that's approaching 0. So this also approaching 0 for the same reason. So we still have 1 here. So really, the whole thing approaches 1. Meaning this really approach 1. Right? So I've proven this. Right? So they're really equivalent during the limit process. So now I can just simply work out this limit. Right? Let me just verify. So what is f1? What is f2? Right? What is g1? What is g2? Right? f1, I say, let me just use 1 minus cosine x. Right? And what's f2? What kind of function is equivalent to this, right, during the limit process as x approach 0? Right? From a well-known limit, I say well-known limit, that is, so 1 minus cosine x, right, this is a well-known limit. My 1 minus cosine x is the double angle formula. That's 1 minus twice of sine square half of x. Right? This is trig identity. So this is just twice of sine square of half of x. Right? And we also know that sine x and x are equivalently infinitesimal as x approach 0, right? So this over that approach 1, right? Same thing. So meaning sine of half of x is equivalently infinitely small, infinitesimal to what? Half of x as x approach 0. Right? So that means if I square both sides, this should equivalent to x squared over 4, right, during the limit process. And so therefore this is equivalent to what? Times 2, right? So x squared over 2 during the limit process. So meaning this is really equivalently infinitesimal to half of x squared. Right? So I can say f2 is half of x squared. Right? They're equivalent infinitesimal. Now, what's g1? Square root of 3 times sine x. Right? G1, F1. Yes. So in this case, what's G2, right? What kind of function is equivalent to this? And since sine x is equivalent to x, right, during the limit process, therefore this is, I can easily say G2 must be square root of 3 times x. Right? They must be equivalent during the limit process. So therefore I have to verify that f1 over g1 does not approach negative 1. Right? So, right, f1 over g1, right? All I have to verify is I have to f2 over g2, right? Like I said, so equivalent substitution, right? f1 over g1. All I have to do is work out f2 over g2, right? f2 over g2, right? Same thing. So f2 over g2. G2, right? So that is what? X half square root of 3. Is it approaching negative 1 as x approaches 0? No. All right, so we're safe. So, yeah. So still we have to not only just substitute this and that, we also have to substitute this and that with something else. Right? So let's just determine e to the x minus 1. Right? Is it equivalent to x? Right, as x approaches 0, equivalently infinitesimal? I say yes. Right, we can easily verify it. This over x, right, approach 1, easily verifiable. We can just use L'Hopital's rule, whatever. So I'm just going to skip over the details. So again, sine x, right, equivalent to x, right, during the limit process. Right? So therefore, we can just, again, we have to verify that does not approach -1, right? So this over that does not approach, is it approaching -1? Right? So this over this, all we have to do is to work out this over this, that is 1, not approaching -1, so we're safe, right? So I just have to replace, like I said, 1 over minus cosine x with this, right? Replace square root of 3 sine x with that, plus square root of 3 x, and replace the bottom e to the x minus 1 with x. Replace sine x with x. Right, we're safe. So that becomes twice of x. Usually it's not legitimate, but under certain conditions, right, like I said, under these conditions, it's safe. Right, so we can cancel out x. Right. What do we have? X approaches 0. Half of x approaching 0. Gone. Square root of 3 stays. 2 stays, right? So approaching half of square root of 3 as x approaches 0. So we just work out the limit to be half of square root of 3. And of course, that is not the only way of calculating it. For example, we can use L'Hopital's rule. Right? We differentiate both top and bottom. Right? So top differentiate, what is it? 0 minus cosine. Cosine becomes minus sine x, minus sine x, its derivative, and plus square root of 3 cosine x. Bottom, what do we have? E to the x differentiate, right? Minus 1 gone. Sine x becomes cosine x, right? So is it still undetermined? So x approaches 0. So this approaches 1. And this approaches 1, right? 2 on so this time we're fine, right? We have 2 on top, bottom. So this approaches 0, that approaches 1. So this time we're fine, right? So 1 plus 1 sine x 0 plus 1 square root of 3, right? So still the same thing, same result, right? A lot faster than the previous method, of course. But it's still fun, still interesting. So basically, any problem that can be solved by using this theorem, I guess, it's always solvable by using some other methods like L'Hopital's rule or maybe Taylor expansion. Right? For example, Taylor expansion, also doable, I think, right? Because remember, when I mentioned at the beginning of the video, I was talking about the speed at which the top or bottom is approaching 0. At exactly what speed? That's what I mean, right? So we can say that x squared approach 0 as x approaches 0, right? Right. Also, x cubed also approaches 0 as x approaches 0. But which one approaches 0 faster? Of course, it's x cubed. Imagine if x is equal to 0.001, right? Then you take the square cube, it's have many zeros, more zeros than the square of 0.001. So this is just a rough estimation, not that rigorous, but makes sense intuitively. right? So what I mean by that is the limit of x approach 0, x cubed over x squared is equal to limit of x 1, right? The top approach 0 faster than the bottom, right? So this has higher speed. So it all comes down to deciding if the top has faster speed or the bottom has faster speed when approaching 0. Yeah, that's what it all comes down to. So roughly speaking, right? So Taylor expansion is what's going to help us determine the exact speed of the top and bottom, right? So maybe let's just, so 1 stays as 1. And let me just expand cosine x first, right? Minus cosine x. Remember, cosine x, right? First term is what? I think it's 1. Right? 1. First term positive, next is negative. So 1. There's even power. There's no odd power, just even power of x's, right? So we have minus x 2 factorial 2, and we have x squared, right? So plus I. Actually, I don't even need this. All I need is I don't even need that, based on my experience, because it'll be enough. Sufficiently enough for me to expand just one term, just one. And then plus little o of just x, right? Not little o of 1, but little o of x, because we imagine we've expanded 2 terms already, right? The first term, second term is 0. But still 2 terms, right? So that's why it's little o of x. So meaning little o of x, meaning that's some function approaching 0 faster than x, right? Little o can be viewed as some other function also approaching 0. So you have infinitesimal times infinitesimal, right? Approaching 0 faster than x, of course. Makes sense. So just plus square root of 3 times sine x, right? Because I can expand it, right? Maclaurin expansion, nearby the point 0. So x approaching 0. Yes, we can do that. So sine x, where do we start? We start from x, right? So we only have terms that has all the power of x's, right? So there's no more even power of x. So first term, second term is minus 3 factorial, then x cubed. I don't even need that, based on my experience. All I need is plus little o of not x, but x squared. But I think x is also fine. It's also fine. All right, because we imagine we've already expanded 2 terms already, right? First term x, next term is 0, but still 2 terms. So little o of second power. Right. So e to the x expanded. First term 1, second term x. Right. And then that's it. That's all I need. Then plus little o of x. Remember, it just represents some infinitesimal times infinitesimal, right? Approaching 0 faster than x, right? It doesn't have to be unique, right? It's just some function approaching 0 times x, which also approaching 0, right? So minus 1 and plus sine x. Again, sine x expanded into x, same as here, right? Little o of x squared, right? So little o of x squared is just some infinitesimal times x squared, right? So approaching 0 faster than x squared even, right? So let me see. This time we should have just 1 minus 1, 0. Minus little o of x. But minus little o of x still equals plus little o of x. Right? It's easily verifiable. So we have little o of x plus square root of 3 times x plus little o of x squared times, I can just put the square root of 3 inside, right? It doesn't matter. So it's just a constant, still equals little o of x squared. Right? But little o of x squared can be combined into this little o of x. Right? It's easily verifiable. Right? Because this function is some infinitesimal that's approaching 0 slower than this guy. Right? Because this guy is some infinitesimal times some higher order infinitesimal, right, than this one. So this one is faster. So, but in the end, overall speed is going to be determined by the slowest guy. This guy is slower than that guy. And when you add them up, this guy is going to drag down, is going to hold this guy back, right? So this is what I mean. So that guy approaching 0 slower than that. So if I have 0.001, right, approaching small enough, you know, so just not rigorously, just roughly speaking. So 4 zeros, right? So this guy somehow is smaller than that guy, right? So roughly speaking, we treat this as this, treat this as that. So when you add them up, what do we have? Zero and 1, right? So you tell me, am I right that the slower guy is going to hold back the quicker guy, right? When you add them up, what's going to make the major impact is this digit, right? 0.001, right? So the following the 0.1 does not make any difference at all, right? The major impact is this one, right? Doesn't matter how quick, how fast this guy approaches 0, doesn't matter. It's gonna still be determined by the slower guy, right? This guy holding this guy back. So just you know, making some intuitive understanding, right? So this guy can be just ignored, right? So just combined already into here, easily verifiable, right? You can verify it rigorously in your own time, you know, just rigorously. But this is not very, very rigorous. So again, we have this. So what's going to happen on the bottom is that 1 minus 1, 0. X plus x twice. Little o of x plus little o of x squared combined together. Again, the slower guy is going to hold back the quicker guy, right? So this guy can ignore it, right? So little o of x, which is also easily verifiable, right? So what we can do now is that we can just divide top and bottom by x. Right? So this x is gone. And little o of x divided by x. Little o of 1. Right? X divided by x, gone. Just 1, right? Little o. This is also easily verifiable. Right? So what this means is that we have some function that's approaching 0 times 1. The whole thing is still approaching 0. Right? So 2, right? X is gone, plus little o of 1, right? So this guy also approaching 0. So 0, 0, we have this over there. And this theorem that I just proved in this video can actually be extended to more general case, where we don't just have 2 pairs of functions. We can actually have n different pairs of functions satisfy certain conditions, similar conditions, and still we can establish the equivalently infinitesimal relationship during the limit process. But like I said, so it seems like any limit problems that can be solved by L'Hopital's rule, for example, I think it can be, any limit problem that can be solved by this theorem can definitely be solved by using L'Hopital's rule. Right? So again, any limit problem that can be solved by using L'Hopital's rule can definitely be solved by using Taylor expansion with Peano remainder, little o. Right, so in the end, Taylor expansion is perhaps the ultimate weapon. Right? So basically, in one variable calculus, any limit problem that can be solved by any other means can definitely be solved by using Taylor expansion. Coming back to the question that I raised earlier. So when I was talking about the speed of infinitesimal, right? For example, this one has higher speed, faster speed than this guy, right? When approaching 0. So now we can easily see that the speed exactly at which this top is approaching 0 at, right? Since we've used Taylor expansion to actually break it down into some details. So in this case, what speed is it? We have square root of 3 plus times x plus little o of x. So it seems like speed is exactly square root of 3 times x, right? The reason is because little o of x plus square root of 3x, if I divide it by square root of 3 times x, I expect it to approach 1, right? The reason is because, and this divided by that is just 1. And little o of x divided by that is what? Little o of x divided by square root of 3 times x. So 1 over square root of 3. Right? So basically, like I said, it doesn't matter even if we have some other constant, right? Our constant times little o of some constant. So little o can be viewed as some function approaching 0. Right? So still this approaching 0. So still approaching 1. Right? So as x approach 0. So really, this guy is approaching 0 at exactly the same speed as this guy, right? So that's what I mean. That's what I'm talking about. So the speed, right? And of course, this bottom, what speed is it? Likewise, it's equivalently infinitesimal to just 2x, right? When x is approaching 0. Right? But it doesn't necessarily have to be square root of, when I'm talking about square root of x squared, right? So in order to find some guy that's approaching 0 faster than this guy, it doesn't have to be x cubed. Doesn't have to be, right? Maybe it can be just s squared times just square root of x. Right? In other words, x squared times x to the power of half. In other words, x to the power of 5 over 2. Or maybe it's this guy. Right? Also, faster than that guy. So, but it can be anything.